Then the energy. We have a solar panel and the built-in phased array antenna of the final rover. We have added another 500 gram into the equation. And then there is a point reserved. One of the tasks defined by the X PRIZE Foundation include an additional payload. The mass will be somewhere between 100 and 500 gram. Yeah, and last but not least, and as I see it's not on the slide, all the parts are held together by a rocket frame made of, finally made of aluminum and carbon. The frame is the most important static element of the rover. A mass of 1 kilogram is achieved. So our mass goal for the rover is now accomplished. Back to Michael.
So, a little bit away from this theory, let's show some video of building a rover.
Soll ich tippen?
Ja.
Okay. Tipp du mal. It's just a placeholder, but it's important. Okay, let's switch to the video. Okay, let's see if we have sound in this. I'm not sure about it.
And now, here for real, our first prototype of a moon rover. So, let's take some look of the details. So, we have here the steering motors inside the frame, the traction motors inside the wheel. You can see here the frame. It holds everything on the rover. Here, this is a case for the electronics. The frame, again, the wheels before built for das heißt montiert. Montage vor der Montage. Okay. The solar panel is just a mock-up right now, but we change that in the next half year. Arne will say in his presentation something more about the technology in the solar panel. And the optics, we haven't decided optics yet, but Schneider Kreuznach seems a big favorite for us. The optics you see here is high-real certified and was used on the ISS space station, and it's very, very expensive. So, what up next year? New materials. We have to look for new materials to reduce the mass for scientific payload. And the idea was to use carbon fiber reinforced polymer, CFK. A new design for the tower and the frame. All that can you see on our homepage and Twitter and the blog. And if you have any questions, today we are standing outside at the booth, and I will be there and will answer. Arne will tell you something about the MCU.
Today I would like to talk about our electronics, especially the main computing unit. Moment. First we have the requirements from the Google Lunar X PRIZE, for example, transmitting the HD video. The main problem is we need a lot of processing power, but also we are limited in selecting the parts. Not all are space compatible. So, we need also a flexible design. For example, we can't change the hardware every time. So we decided to use that FPGA. The condition is that it has to be high-real certified, so it will work also in space. One lifetime has two definitions. One is it has to live long enough on the moon. The other is it would be nice to reuse the design for later missions. So keep it simple and stupid. So don't add too much parts, not external video compression chips. So. What is high real? That means first we have extended temperature ranges. The standard high real chips are from -55 to 125 degrees. That is still not enough for the moon, but it's the best you can buy here. So it means we have to test these parts if they can withstand the -160 degrees or at least the 122, or and for the worst case, the 160 degrees. There's also the radiation. High-real components are tested against radiation. For example, we have the single event effects that are electrons or protons with a high speed that hits the chip. And in worst case,